The next important use case for access network is what is called as the front haul network, and of course the backhaul network in wireless networks. Now, what is this front haul network? So you know that whenever we make a communication from one cell phone to the other, especially when the sender and the receiver, the person who's making the call and the person who's receiving the call are at two widely different geographical location. What happens is, from the user equipment through the wireless channel, the data goes into what is called as the remote radio head, which is your antenna. And from the remote radio head, there is a baseband processing unit which basically takes out the baseband data from your radio frequency, and that is baseband data is passed on to the core network. Okay. Now, typically in until 2G kind of implementations, this baseband unit and the remote radio head were co-located in the same. So the baseband unit and the remote radio head were co-located in the sense that the baseband unit was a part of the tower. But now, as your data rates are increasing and the kind of processing that we are doing is changing and it's becoming faster, what has happened is that the physical location of the baseband unit is moved away from the remote radio head. And this is what is called as a centralized radio access network architecture, or the CRAN. CRAN stands for centralized RAN or a CloudRAN. So where the different network functionalities are actually controlled by the central station, which is a cloud. Okay. So the concept of CloudRAN, this is picked from China Mobile. It's like this. So you have the different users which are being serviced by this remote radio heads, and as the user moves from one location to the other, it's not the user equipment which is trying to follow the tower. The way it works is the towers actually follow the user equipment to give a very seamless connection. Okay, so this is like a collaborative radio where there is an advanced internet interference management. So as this user equipment moves from one zone to the other, depending on where you are getting your minimum interference, the corresponding RRH will service the user. Where are all these decisions made? These decisions are made in a centralized server. So there is a virtual base station pool, which baseband pool, which actually computes. So there is a real-time cloud computing happening. Decisions are done, and different RRHs are servicing the user, right? Which means the data rate between this baseband units, which is servicing this different RRH, is there is a requirement for a large data rate because there is a constant communication. Not just that, different RRHs are getting serviced by the same baseband unit. This is good because if this baseband unit is servicing only one RRH, the resource is limited and it is actually not a cost efficient way of doing this. And the new standard that is developed in the wireless community to allow interoperability in different equipment manufacturers is called as CpRe. CpRe is centralized. So the different manufacturers for the radio equipment should agree upon a standard that is being followed universally. So different equipment manufacturers and network operators have gotten together, and they have come up with this new standard, which is what is called as Common Public Radio Interface. This is available as an open source. So any transmission that happens between the the radio equipment and the equipment control, which is like the remote radio head and the baseband unit, is carried out through the encapsulation, which is decided by this standard. So remote equipment control all functions in the baseband domain, whereas this the radio equipment control basically operates in the baseband domain, whereas the radio equipment itself is referring to the antenna, the power amplifier, the local oscillator, the RF generator, the high frequency generator, etc. So the radio equipment refers to the location of the antenna, where the high frequency is generated, the data is baseband data is modulated, and then it is power amplified and transmitted. Okay, so the interface between them, between your antenna and your baseband unit, that interface is through a optical link now, and that optical link is the framing there, or the protocols there are following what is called as the Common Public Radio Interface, CPRE, most commonly followed standard. Okay, and so let's take the example where I have let's say 4 antenna sectors. So we are trying to figure out what is the data rates that are required in a CPRE link, right? So let's take the example of LTE, right, which is your 3G communication. The bandwidth is 20 megahertz. Your center frequency is something like let's say 2.5 gigahertz or something, right? And the bandwidth is of your information is 20 megahertz. And let's say that is fed into radio equipment, which is having 4 sector antennas, which means it's facing in 4 direction. And let's say each antenna is a 2x2 element to so you know that in wireless technology you have the concept of multiple input, multiple output, where the same information is fed into 2 antennas and you kind of co-process to get the best out of it. So each of this has 2 antennas, which means that there are totally 8 antennas, because there are 4 sectors with 2 antennas each. And in the our radio equipment control point, where your baseband data is generated, you are familiar that in wireless technology, the modulation done is not QPSK or 16-QAM directly. They use what is called as a multi-carrier modulation. Let's say OFDM is the most orthogonal frequency division multiplexing is the modulation scheme that is used in most commonly in wireless technology. So in this REC, what really happens is the baseband data is generated, and the I and the Q of the baseband data is generated. So a typical OFDM waveform in the time domain, let's say, looks like this, right? So in OFDM, your modulation happens in the frequency domain, and then you do an inverse Fourier transform. So you get your time domain signal that needs to be transmitted, and it has an in-phase and quadrature component that needs to get transmitted. So remember, this is just the baseband. So you're talking about transmitting a 20 megahertz bandwidth signal from the BBU to the remote radio head. And the remote radio head requires this data for 8 antennas. Okay, they are all time division multiplexed and sent. So how is this done? So you have 20 megahertz bandwidth, and you have a specific sampling rate depending on the bandwidth. And the sampling rate typically is a multiple of the Universal Mobile Transmission System rate, UMTS rate. UMTS rate is 3.84 given by the chip there, electronic chip. So 8 times comes closer to 30.72. So that's good enough for servicing a 20 megahertz bandwidth, which means to cut the long story short, you have a sampling duration TS, which is 1 over 30.72 megahertz. Okay. What you need to transmit looks like it's like an analog like signal, because it's an OFDM signal. So which means that you have to sample and then you have to quantize. So the signal goes through analog to digital converter, And in order to maintain the quality of the signal, you do a 15-bit quantization. Now, 15-bit quantization would mean that every sample now gets represented as a 15-bit, and you do have the I in phase and the quadrature component of the data, which means that the total number of bits per IQ sample is 15 plus 15, 30, multiplied by 8 because you want to send the information for 8 antennas. So, the total number of bits that needs to be transmitted for every sample is 240, and your sampling rate is 30.72 to support 20 megahertz. So, the data rate is roughly 30.72 multiplied by 240, that comes to about 7372.8 Mbps. Okay. Now, this is not considering encoding. So, typically you also have, you encode your data so that any errors can be corrected. So, you take a simple 8-bit, 10-bit encoding, which means that to transmit every 8-bit, you are actually transmitting 10 bits. The remaining 2 bits are used for encoding. So, for that, assuming that simplest 8B, 10B kind of encoding, the approximate data rate will be 7372.8 Mbps multiplied by 10 divided by 8, and that is this approximately 9.2 gigabits per second. This is a very, very large data rate, considering the fact that you are transmitting only 20 megahertz worth bandwidth. To transmit 20 megahertz worth bandwidth, the CPRE standards, this is calculation based on CPRE standards, are requiring us to have a transmitter which is capable of doing an optical transmission of approximately 10 gigabits per second. Now, what if you are now advancing your technology to 4G or to your 5G, where the bandwidth is now not 20 megahertz, it could be 100 megahertz or it could be even 400 megahertz. This data rate that is required for a simple 4-sector antenna, this is just a 2x2 MIMO system. You could have increased multiplicity, you could have increased number of antennas, in which case the data rates that are handled by this remote radio head to the baseband unit, so this is REC or baseband unit to the RRH, which is having all this, this data rate is really staggering. Which means we always thought that the gigabit transmission happens in the long haul network. It turns out that the gigabit transmission is actually happening in each tower of your cellular communication. And this data rate is only going to progressively increase, which means that the technology that is required at the front haul, short distances, these distances could be anywhere between 100 meters to maximum of, let's say, 2 kilometers. That's where you need a lot of active optical cable research, and you cannot really think of using a very complicated signal processing in the optical domain simply because the power consumption in each of these mobile towers are going to increase just because of this, right? So, the current CPRE rates is again available in the open source from the CPRE website. They have given data rates up to, so here you have 10 Gbps and you have data rates up to 25, roughly 25 Gbps, and following the kind of Ethernet way of packaging the information. And this is only going to progressively increase as we move on to more evolved or more advanced cellular technologies. So, the bottom line is that the spectral efficiency, the data rates that needs to get supported by the optical link, whether it is short distance link or it's a very long distance link, is only increasing, and the technologies are in the fiber optic communication domain are continuously going to further increase, right? So, the CPRE standards are still evolving to handle the large data rate. The other possible thing that is being researched, mostly in the research community, is being investigated is, instead of digitizing the entire data, can we transport it to the radio head in the analog domain itself, right? So that gives us to the idea of, leads us to the idea of radio over fiber, and that is of course a topic for another course on microwave photonics. Now, microwave photonics deals with technologies where the microwaves, which could be anywhere between 2.5 gigahertz to about 100 gigahertz frequencies, are transported with the help of, are either generated, transported and detected with the help of optical technologies. And these have been traditionally used in scenarios which are using these high frequencies, which are primarily radars. But it turns out that with the next advancement in wireless communication technology, we are going to be using 28 gigahertz and 56 gigahertz kind of frequencies, carrier frequencies for even wireless communication, cellular communication. So in that scenario, in addition to the digital communication technologies supported by the optical fiber, we need to now look seriously into analog communication through optical fiber. And as I said, that is a topic for another course. So I hope you enjoyed the course, and of course we can interact during the weekly interaction sessions. Thank you.